buckling of struts experiment. And what we're looking at there is the behavior of a beam loaded end to end such that when the beam is loaded beyond its capability, it will start to bend to the side. And we have a formula for computing what we can expect the performance of that to be. We're measuring the force that we apply to the end of the beam, working in this case from long to short. So this beam is 520 millimeters long. We're going to, as we load it, I'm increasing the load on the beam, and as I do, the measurement continues to increase as it, and you notice that it pops all at once in this case. So we'll run this again to see the point at which it starts to deflect. And as we add load, the beam begins to deflect and will not take any additional load. So at that point, we're dealing with a buckling load of 30 newtons. I'll take this out. Go to a shorter strut. And with a shorter strut, we should experience a little bit more buckling load because the response will be more concentrated. And again, you see I start the bow at 37 newtons. Buckling load is 54 newtons. Load it slowly. And as I add load, it stops taking load, so I'm at 62 newtons. Starting with no load. And we add load. And as I add load until it responds by buckling rather than accepting more loads, and I'm running about 26 newtons. For the second part, our setup involves a fixed connection at one end as opposed to the pin connection at the other end. We're free to rotate here, we're fixed here, so that rather than simply having a direct bowing, we're going to have something that looks more like a question mark, because we'll be constrained on this end that we can't really bend freely. Here we can bend freely. So we'll look and see how that affects our ability to bear load. So we start for the shortest strut. That length goes from 320. Notice that on the table it goes down from 320 to 300 because I'm taking 20 millimeters off on this end because I'm measuring from the point at which it becomes free. So we add load to it. Continuing to increase load. It's continuing to take load. And equilibrium is taking about 132 newtons. At our load. My load maxes out at about 146 newtons down to the pin connection point. Here the strut is riding in a V groove, so it's free to rotate on the bottom. It is not free to rotate at the top. So instrument is zeroed. Continue to add force. And our maximum force is running about, let's continue to take a little more. About 95 newtons. So we add load. And you can see it beginning to deflect. Maximum load is running about 83 newtons. And we put a load on it until reached our maximum load, which is about 68 newtons. That maximum load is our buckling load for the strut. We are mounted now, fixed top and fixed bottom, and we add load. And here our deflection is sort of a bell curve because we're constrained on this end. We can bend out, then back, then back, then in. The maximum load is running about 56 newtons. Okay, we continue. We've got the second strut in here, which is 430 millimeters long between connections, because remember the strut shortens 20 millimeters. It's 470 at the beginning for this strut, less 20 at the top and less 20 at the bottom. So we have the net of 430. We add load to it. And our maximum load is going to be around 70 newtons. For strut 3, the effective length is 380 millimeters. We add load. Our maximum buckling load is somewhere about 150 newtons. The fourth one we're doing is strut number 2, which is 330 millimeters effective length. And we load slowly. You begin to see the deflection of the beam. And our maximum load is peaking out around 220 newtons. Okay, again, restrain top and bottom. This is the shortest strut with an effective length of 280 millimeters. And we head load. We can see deformation, but it's still taking more load. In the range of about 98 newtons. Okay. That gives us the data for the second experiment on the buckling load, and concludes that portion of the experiment. There will be some notes for you along with the lab rubric, and you can do the calculations accordingly.